Hello everybody and welcome to this week's video. This will be the beginning of my series on differential geometry for physicists. It is a core syllabus thing that I've put together over the last couple of weeks. It is a 10 lecture series that intends to get you from what on earth is a manifold to things like fiber bundles and the Riemann curvature and things like that. Um, so I'll start off with a spiel, and then I'll talk about what the course will cover, and then I'll talk about some prerequisites, and then we will begin the first lecture. Um, well, differential geometry. First of all, um, it's really important for modern theoretical physics. I mean, thinking of things like general relativity, which is described through the space-time curvature is described through manifolds, and how we work with those manifolds is really important. Same thing with the standard model. Those are articulated over smooth manifolds. And the aim of this is not to teach you uh, not to have you, prove why a manifold by definition is Hausdorff and second countable. Um, it is it is to give you practical skills that you can use in physics regarding differential geometry. So this is the first lecture, which will concern what manifold is. We'll look at charts, atlases, and smooth maps. Next week, week 2, we will cover tangent spaces and vectors as derivatives. Week 3 will be dual spaces and one forms, differential one forms. Week 4 will be tensor fields and metrics and metric geometry. Week 5 will be exterior algebra and differential forms, so not just one forms, and then Hodge duals and Maxwell's equations in 2 lines will be week 6, which is a interesting one. Maxwell's equations in 2 lines meaning 2 equations. We will look at integration on manifolds. This is the 7th lecture. Integration on manifolds and the generalized Stokes theorem across topology, and then we will look at covariant derivatives and affine connections. Week 9 we will look at torsion and the Riemann curvature tensor, and then in week 10 we will look at fiber bundles and gauge theories. So yeah, that's an overview of what the course covers. In terms of prerequisites, it is very important that you are comfortable with multivariable calculus. What is a partial derivative? How do we do things like the chain rule in R to the n? How do we do multiple integration and like basic classical vector calculus, dot products, cross products, that kind of thing. Another very important thing is linear algebra, understanding vector spaces, dual spaces, linear transformations, change of base, and the sort of idea of our inner products and our like metric structure. And then it is also kind of useful to have a basic intuition of real analysis with things like what does it mean for a set to be open or closed? Can you understand continuity through an epsilon delta definition? And what does it mean for a function to be C infinity or smooth? Things like that, basic real analysis stuff. So with that, we will begin. And we will begin by looking at the smooth manifold, which is kind of the foundational object of field theory, which is a really important part of physics, modern physics, field theory basically. So I mean, you first learn about curved surfaces maybe in secondary school in America if you're doing an AP in calculus or something. You probably learnt about it, or AP geometry. I don't know if there's AP geometry actually. I've never really looked into it. I know there's AP calculus BC, where you definitely do spheres and stuff. Oh, in pre-calculus you do 2D stuff. I don't know if you do 3D. Um, but you'll learn about curved surfaces like spheres, hyperboloids, things like that. And you your instinct is sort of to view these as embedded in a higher dimensional flat space. It's like a 2D surface, right? It's like a flat 2D surface that just exists in 3D geometry. That's called extrinsic geometry. But if we look at something like general relativity, right? Space-time is the unit. It's not like there's a fabric just on it is very much as space-time curves and changes, the universe curves and changes. So you can't treat this the same way as we treat those kind of um, extrinsic shapes. Sorry, it's something on my nail. This is remaining on my nail. Well, yeah, there's not really a higher dimensional superspace that all of the universe floats inside of. So what we have to do then is define our geometry intrinsically. So rather than it's like, for example, say you're a person on the sphere and you perceive the sphere as flat and you don't know that the sphere exists in a higher plane of geometry, except it's not like that because space-time does not exist in a higher plane of geometry, it exists in its own geometry. So we have to define space-time through its own dimensions, purely then from measurements made inside of space. Inside of, yeah, that space-time. So how do we do that? Well, we use a manifold. If you were in a manifold, at some point, we say it would look locally flat at that point, um, which lets us sort of build calculus without referencing a surrounding embedding like space. So we'll begin by putting some definitions to things. So yeah, the aim of this differential geometry is to transition from this extrinsic view to the intrinsic view. Before we do like calculus and stuff on this, we kind of need a topological space that behaves locally like a flat Euclidean space. We just need a little area, a little neighborhood, to look like Rn. Like, for example, if you're living on a sphere, it looks flat around you, even though it's a sphere. And we do that through a topological manifold. And we say this is a manifold M. In fact, I'll write an n dimension manifold M. And M has to satisfy a few conditions. So M has to be Hausdorff and second countable. Well, these are some weird words. What are Hausdorff and second countable? What does it mean to be first countable or second countable? Well, these are sort of technical conditions from algebraic topology. Hausdorff is this guarantee that distinct points can be separated by non-overlapping open sets. This prevents any pathologies like one point splitting into two. And second, countable. It ensures that our space isn't unreasonably large, which means that we can cover it with a countable number of coordinate patches. Again, these are kind of fairly abstract ideas. We can write this in a mathematical manner. A manifold M satisfies the following. One, M is locally Euclidean. So for every P in M, there exists. I'm just gonna write it in English. there exists an open neighborhood U subset of M and a homomorphism. And a homomorphism phi, which takes U to V subsets of Rn, or essentially there's a continuous bijection with a continuous inverse. And this implies that, or this shows that M is locally Euclidean. So for some small neighborhood around P, it appears to be Euclidean. Our second condition is that M is Hausdorff. So if we take any 2 points P, Q in M, there exists open sets UP and UQ, such that P is in UP, Q is in UQ, and most importantly, UP and UQ are the empty set. Thus, there is no intersection. I'm going to change that very clearly to be intersection, because actually that sign means something that we will learn at some point in the future. Yes, there is no intersection between UP and UQ. And the final one, 3, is that M is second countable. Cool. So we have defined a manifold, and I think the key understanding here is that a manifold acts as if it's in Rn in a local neighborhood, but overall in the open neighborhood it forms a shape. Thus we are able to treat it as if it's in Rn in a local area, and not if it is not. So M is in an abstract set, so we can't really do any calculus on it yet, which is annoying. We want to do calculus on it. So what we can do instead is use something called a coordinate chart. And a coordinate chart allows us to flatten out a region U in that manifold onto an open subset of Rn. So this is what allows us to take our local neighborhood, which resembles Rn, and turn it into a real coordinate system. So let's take a chart, chart U phi. We'll assign n coordinates, n real coordinates, x1, x2, dot 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 to xn, onto P in U. And we have a map. Our map phi is a map, or which is sort of translating our abstract geometry on M into our regular vectors, which we know how to integrate and differentiate. So a single chart cannot cover the whole space, right? Because then it is no longer a local neighborhood. If we had a region U that covered the whole space, it would be the manifold. And we know that the manifold does not resemble R. Only locally does the manifold resemble Rn. So we have something called an atlas, which is a collection of charts. For anyone who doesn't know where this lexicon comes from, well, charts are the name for nautical maps, and you'd have or just generally maps. I mean, I know them from I'm a sailing instructor, so I'm aware that they're the name for nautical maps, but I'm sure other maps have been called charts in their lifetime. If you have a collection of charts, you have an atlas. If we have I've already kind of defined what this is, but we can more formally set out that we have some phi which maps U to Rn, which is a homomorphism onto its image. Phi, thus phi of U is in Rn. And again, we can then say phi of P is equal to x1 P, x2 P, all the way to xn P in Rn. And we have a family of charts A. It should really be like a curly A, like that. That's quite good. Which is this set of U indexed set of U's and I's, indexed set of charts. In other words, that covers Ni being here a member of I, the total, or rather the set of indices, in indexes that covers I forgot to close that, sorry. And we have that this total union of I in I of our UI is equal to M. And this is an atlas. Atlas. Like the mountains. So far we have defined a manifold, said that manifolds have to be Hausdorff and second countable. And then we have defined a chart, which is something that can map a neighborhood onto Rn. And using an atlas, which is a indexed set of all of the charts, here it is, this is our set, of all of the charts over a manifold, we can translate the entirety of a manifold to be Rn without breaking our rules of being second countable and Hausdorff. Now, this is a really critical question that we're about to encounter in differential geometry. If two different observers, if two different observers construct coordinate charts, one of them's UI, one of them's UJ, and these overlap on the intersection of UI and UJ. How do we ensure that these two agree on physics? How do we make sure that they're not telling us different things and overlapping and thus causing a contradiction? So if we take a point P, which is on this intersection, UI intersect UJ, this will get assigned coordinates in Rn by observer I, but then by I, but then it will be given coordinates phi j p in Rn by j. Now we need a very important thing which is called a transition function, and this allows us to map directly from observer I coordinates to observer j's coordinates. So we have a transition function and we can call it phi ij, not comma, sorry, phi ij, which is phi j compose phi I inverse. Now, something that is fairly useful here is phi i's coordinates are all in, this is in Rn, and this is in Rn. So, all that phi ij is doing is mapping Rn to Rn. This is just standard multivariable calculus. So now we know what it means for this to be infinitely differentiable, because this is C infinity. If all of our transition functions in an atlas are smooth, we then call this manifold a smooth manifold. And the transition functions will be for any two observing points. And we can formalize this for overlapping charts. phi j compose phi I inverse phi I ui intersect uj to phi j ui intersect uj, that being our p, where these are both in these are both members of iron or Euclidean geometry. So, and just to formally define what a smooth atlas and a smooth manifold are, A, that was terrible, A is C infinity smooth if all phi ij is smooth. And just as a side point, be aware that a smooth manifold is topological, is a topological manifold rather, equipped with a maximal smooth atlas. That's all that means. This is all being very abstract, and I'd like to make it less abstract with an example upon which we can apply our ideas about smoothness and transition maps well. This is something that I've brought up before, which is a two-sphere. Well, what's a two-sphere? Well, a sphere is notably three-dimensional. But what we'd like to do here is make it or we'd like to make it we'd like to make it we'd like to define it intrinsically. So first of all, we'll define a two-sphere. So S2. This is going to be defined by the following. So x, y, z be our coordinates in r cubed, defined by the equation, the set of points defined by the equation x squared plus y squared plus z squared equals 1. This is, of course, our unit sphere. Can we cover s squared with a single coordinate chart? No, we cannot. Topologically, we cannot. But we can cover it with two charts using stereographic projection. If we project the North Pole onto a plane at the equator and the South Pole onto the plane at the equator, onto the same plane rather, the equator, then we can use stereographic projection to double map it. So we'll work through this. We'll look at chart 1 first. So we'll let n equal to 0, 0, 1. This be our North Pole. And we'll have u sub n be s squared by the set of n. Now, if we were to take any point and project it through n onto the plane, we have the following: phi n x, y, z be x over 1 minus z, y over 1 minus z, which is equivalent to some coordinates u, v in Rn. I'm running out of whiteboard space. And then we can look at our inverse map, which is going to map back to, sorry, this should be r squared, importantly, because this is r cubed and this is r squared. So now we can map back to r2 through phi sub n inverse. uv is going to map uv in r squared back to s2. And let's now look at our coordinate projections from this in terms of u and v. Well, we have x is 2u over u squared plus v squared plus 1. Again, you can derive this from this by rearranging simply and getting everything, plugging it in terms of u and v. Y is 2v over u squared plus v squared plus 1. Of course, they're identical. And z is u squared plus v squared minus 1 over u squared plus v squared plus 1. Now, if we go to look at the south pole projection, we can do the same thing, except it's going to be equal to 0, 0, minus 1 be our south pole, and we have u sub s be s2 per the set s. And if we're again to project our p, x, y, z through s, we get similar-ish thing as the north pole. Note instead it's x over 1 plus z, y 1 plus z, as opposed to our 1 minus z from before. And this is going to be u tilde v tilde, which are members of r squared. And of course we have the same thing as before. We can then translate back using, or we don't need the inverse function here actually, because if we recall our overlapping area, so this is going to be un intersect us, and this is going to be s squared per the set of n s, and we can evaluate our transition map. First of all, let's figure out what u tilde is. So it's x over 1 plus z. At this point, you plug in our values for x and z. I am not going to work through that algebra because it's a waste of time. It's u over u squared plus v squared, elementary algebra. V tilde, same thing here. It's y per 1 plus z. This is going to be v per u squared plus v squared. And so we can now look at what the composition of this is. If we were to take a vector, u, or rather, I'm going to stick to underlining for this series because it's useful for a bold. This is going to be uv. We now see that the composition of the inverse and our phi s rather, on u is simply going to be u over the absolute of u squared. Well, what is this? It's an inversion in the unit circle. This is infinitely differentiable, c infinity, so this is c infinity for u that is not 0, 0. Of course, this is an R2, and this corresponds perfectly to our domain, which is r squared over 0, 0 would not work because it's a division by 0 error. So if in R2 c infinity holds, then S2 is a smooth 2 manifold. Wonderful. So, well, let's do a little recap before I finish. We have a manifold M. This is an abstract space that is homeomorphic to a flat Euclidean space Rn in a local neighborhood. Then we have our chart, which is a local coordinate map that maps a neighborhood to Rn, which assigns numbers to our abstract points. Then we have an atlas, which is a collection of our charts, and then we have our transition function. And our transition function matters because we use the transition function to define a smooth manifold. That is, when the result of our composition of the transition and the inverse transition of our two perspectives on this manifold map Rn to Rn, then we define a smooth manifold. Yeah, so this is the introductory sort of lecture on differential geometry for physicists. I hope that this has been an enjoyable lecture. I'm not quite sure on what part to end. I'll just leave it at the bottom. But yeah, I hope that this has been useful, and as I said, next week's video will be on tangent spaces and looking at vectors as derivatives. Until then, I hope you have a very nice week, and I'll see you then. Goodbye.